We will start chapter number 8, water treatment. So, what is the meaning of water treatment? It is the recycling of the water that you're going to be using it later on to drink or to cook or to take a shower or to also clean. Let's look at this. The purpose of water treatment is to provide a potable water. Now, I'll give you the definition of potable water in a few seconds. That is palatable. So this is the scientific definition of the purpose of water treatment. Provide a potable water that is palatable. So what is potable water? Potable water definition, it is a water that is healthy for human consumption. So this is one of the definitions of potable water. Healthy for human consumptions. And also free of any harmful microorganisms and organic matter and also inorganic matter. All of these microorganisms, organic, inorganic, if found in water, can cause adverse physiological effect or, of course, do not taste good. So, again, the purpose of water treatment is to make the water potable, to provide a potable water. Potable water means water that is healthy for human consumptions and free of microorganisms, free of organics, and free of inorganics. Of course, if these organics and inorganics and microorganisms are found in water, this will cause adverse health effect. Now, this is definition of potable. What is palatable? Palatable, it's to make the water aesthetically acceptable to drink, or free from turbidity, free of color, free of odor, and objectionable taste. So, of course, potable is more important. Palatable, it's in the second rank of the purpose of the water treatment, to make it palatable. It's aesthetically acceptable to drink, free of turbidity, color, odor, and bad taste. In the developed countries, they are treating water for both potable and palatable. Of course, they care about health and they care about no turbidity, no color, no odor, and no bad taste. But some peoples, they don't like the palatability of the municipal water. And this has given everyone to use a household point of use. For me, I don't like the palatable water of my municipality because I could see some error. I could see some corrosivity inside the water. Okay? I could taste the bad taste in the water. So I use household point of use. My household point of use is reverse osmosis. And we will be talking about this in the next few slides. So some people, they don't like the palatability of their municipality water. They use a household point of use treatment system. And some of them, they use bottled water. What is the characteristics of the untreated water? Of course, everyone expects drinking water to be clear. You don't expect the water to be having some color. Of course, colorless, odorless, no smell, and free of harmful chemicals and pathogenic microorganisms. Every consumer, everybody expects these things to be inside the drinking water. But the problem is that natural water like rivers, lakes, and all of this like that, they usually contain some degree of dissolved particulate And of course, they should have some degree of microbiological constituents, which all of these are obtained from the surrounding environment. Let's look at table 8.2 that summarizes the important chemical and biological constituent found in water. General classification, major inorganic constituent. Now, what are the major inorganic constituents that might found in surface water? Calcium is one of them. Chloride, fluoride, iron, manganese, nitrate, sodium, silver. The typical range for these is 1 to 1,000. This is from the surrounding environment, either from the soil at the bottom of the river, lakes, or whatever. This is the major inorganic that might find in water. The minor inorganic that might find in surface water is cadmium, chromium, copper, lead, mercury, nickel, zinc, arsenic. The range is from 0.1 to 10 microgram per liter. And there is something that might find in surface water called naturally occurring organic compound. We call them NOM. Okay? Naturally occurring organic matter, NOM, that is measured by the total organic carbon, 0.1 to 20 milligram per liter. There is also some concentration of anthropogenic organic constituents like synthetic organic chemical, SOC, and emerging chemicals of concern used in the industry, of course household, agricultural like benzene, methyl butyl ether, and tetrachloroethylene, trichloroethylene, and vinyl chloride, and alcohol. Of course, these anthropogenic organic constituents below 1 microgram per liter and up to the tens of milligram per liter. Or the last one, living organisms, bacteria, algae, and viruses. Of course, the count is over millions. Table 8.1 is the physical characteristics of natural water. How could you measure it? It's by measuring turbidity, particles, color, taste and odor, and temperature. Turbidity, it's a measure of what? It's a measure of the optical clarity of the water. And of course, this turbidity is caused by the scattering and the absorbance of light by suspended particles in the water. So if you have a tank and there's particle, and this tank is full of water, there's particle, these suspended particle, when they absorbed the light, okay, this is turbidity. This is the measurement of turbidity. And there is a device to measure turbidity called a turbidity meter, which is used to measure the interference of light passage through the water. Turbidity is reported in terms of NTU. That is the unit of measuring turbidity. Okay? And of course, the World Health Organization, now we know this is the famous organization, WHO, reports that turbidity is less than 5 NTU. This is usually acceptable, but may vary depending upon the availability and the resources of the treatment. In the United States and America, many water utilities aim to treat the water to less than 0.1 NTU. Very tough, but they make it. This is turbidity. Particles. Particles in natural waters are solids, larger than molecules, but generally not. You can't distinguish them by the eye, by the unaided eye. You need a microscope, you need some magnifying lens to look at this. These particles, the problem with these particles that they may absorb toxic metals. I know that you might have some particles in water, and these particles that you drink them, they might have some toxic chemical inside, showing some toxic chemicals, all synthetic organic chemicals. Of course, the water treatment considers particles in the size range of 0.001 to 100 micrometers. Particles larger than suspended solid. So higher than 1 micrometer is called suspended. It's still suspended in water. While particles between 0.001 and 1 micron can be considered colloidal particles. So there is a differentiation between suspended particle and colloidal particle. Okay? Constituents smaller than 0.001 micrometer are called dissolved particles. So there is suspended with a range of sizes. There is colloidal particles. At the end, there is dissolved particles. Of course, natural organic matter that we talked about in the last few seconds. This comprise colloidal particles, dissolved organic carbon, DOC, and of course this DOC is a portion of NOM that can be filtered through a 0.45 micrometer filter. Characteristics is color. Color is imparted to water by dissolved organic matter. This is what makes the water colored, the dissolved organic matter. And the natural metallic ions such as iron and manganese and turbidity. This, or most people can detect color at more than 500 true colors units for water in a glass. So this is the unit for color. Taste and odor can originate from dissolved natural organic or inorganic constituents and biological sources present in raw water. They can also be an outcome of water treatment process. Last, temperature. The surface water temperature may vary from 0.5 Celsius to 3 Celsius in the winter and 23 Celsius to 27 Celsius in the summer. Groundwater can vary from 2 to 25 depending upon location and well depth. So these are all the characteristics of the natural water that we should analyze all the time. So the first characteristic, turbidity. Low turbidity measurement, less than 1 NTU, are typical for most groundwater sources. Well, if you are dealing with surface water, turbidity varies depending on the source. Of course, groundwater is a very good, the soil around the groundwater is, inside the aquifer is good for filtering the water. In lakes, reservoirs, turbidity is usually stable and range from 1 to 20 NTU. But also the seasonality, winter versus summer, rainfall without rainfall, this also change this measurement of turbidity. And of course, if you have algae activity, that also might change this range. Turbidity in rivers is highly dependent on, of course, rainfall, precipitation, and can range from 10 NTU to more than 4,000 NTU because of rain coming in, disturbing all the soil and making all this soil particles suspended in the river. Turbidity measurement are primarily used for process control, regularity compliance, and to compare it between different water sources. And of course, turbidity is a very good indicator of increased concentration of microbial water constituents, such as bacteria, Cryptosporidium, oocysts, and Giardia cyst. The next is particles. This is found in natural water and can be measured in terms of the number and size. You could number it. You have 5, you have 100, 1,000, and you size it. 100 microns, 50 micrometer. Particle removal is important in this step because it has been suggested that if particle found in water, there's Giardia and there is Cryptosporidium cyst in water. So you have to remove particles. You have to remove particles because if you remove them, which means that you are removing all these in water. Suspended particles such as algae, organic debris, protozoa cyst, and silt can be removed by conventional sedimentation. You're allowing the water to settle. You're allowing the water to go down in the tank. Sedimentation. And of course, depth filtration method. It's either you are allowing the particle in the water to settle, and we call this sedimentation, or you are allowing it to go through a filter. So the filter will grab this sediment or this suspended particle from the water, and the water will go down clean. There's other processes like called coagulation, flocculation, and these processes can remove colloidal particles too. The problem here is that many dissolved constituents will remain in solution, okay? Such as the lower molecular weight natural organic matter in OM, for example, humic and fulvic acids and synthetic organic compounds. There's other treatments available like activated carbon adsorption and my favorite one, reverse osmosis. This might use to remove these colloidal and dissolved constituents. Color is categorized as the apparent or true color. The apparent color is measured on unfiltered samples. So that's why they call it apparent color. So it includes the color imparted by turbidity. You don't filter it, you just measure it, and the color imparted by turbidity. True color is measured on water sample passed through a 40 millimeter filter. So it is a measurement of color imparted by dissolved constituents. So there is apparent color and true color. True color is through a filter. This color doesn't mean that there is a health impact on humans. It can mean that there is some aesthetic problem for some individuals. Okay? And of course, some communities, treatment is usually provided. We need to provide good, tasty, and no color water. Next one, taste and odor. The most prevalent natural odor causing compound in surface water come from the decay of algae. Okay? So for example, this decay of algae will produce gossamin and methyl isoprene, which impart a musty odor at concentration as low as 0.000005 milligram per liter. Very low concentration, this musty odor. Okay? Water treated with excess chlorine will have a chlorine odor too. If you put too much chlorine in water for disinfection, you'll have a tasty that comes from chlorine odor and a smell that comes from chlorine odor, which can be detected as low as 0.01 milligram per liter. And of course also water containing dissolved inorganic compounds such as iron, manganese and copper may have a metallic taste. The taste of reduced iron, Fe2+, can be detected at 0.04, 0.01 milligram per liter. And the taste of the reduced manganese, Mn2+, can be detected at 0.4 to 30 milligram per liter. There's a lot of natural synthetic organic compound will impart an objectionable taste to water. Example of these include phenol, which can be detected at a concentration of 1 milligram per liter. Temperature. Water temperature is very important because it affects many physical and chemical parameters of water, such as density of the water, viscosity, vapor pressure, surface tension, and solubility and reaction rate. And of course, all of these can be used to design and operate a treatment plant and the pipeline system. So now we'll go through the major and minor inorganic constituents. Calcium is the first one. This is the most abundant cation found in water and is the major constituent for water hardness, along, of course, with magnesium. Calcium greater than 60 milligram per liter are considered not good. Next, chloride concentration. It can vary from 1 to 250 milligram per liter. Of course, this depends on the location of the water and the typical surface water, which is usually less than 10 milligram per liter chloride. If you have a water body that is affected by the salt water intrusion, and of course groundwater that contain trapped brine, this is like brackish water, may have chloride concentration similar to the ocean itself. Next, fluoride, which exists in natural water primarily as an anion F-. But this can also be associated with ferric ion, aluminium, and beryllium. And of course, some water utilities, some water treatment plant, not here in Kuwait, the treatment plant here in Kuwait, they don't add fluoride, but some water utilities in the US, they add fluoride in the form of sodium fluoride or hydrofluorosilicic acid at a concentration of 1 milligram per liter to prevent tooth decay. Of course, iron is the next one, which is an abundant in geological formation and frequently found in water. Iron, if not found, can impart a brownish color to laundry and bathroom fixtures. The concentration of 0.2 to 0.4 milligram per liter. Manganese can impart at that concentration an unpleasant taste to the water and stain laundry and fixtures. Also, a very important thing that might find in surface water is high concentration of nitrate and, of course, other forms of nitrogen from urban and agricultural runoff because of the use of the fertilizers. Groundwater can also contain high concentration of nitrate, especially in agricultural area because of this leachate or this fertilizer that's leaching toward the groundwater. Of course, ammonia fertilizers are biochemically converted to nitrate in the soil or areas impacted by on-site treatments such as faulty septic tanks. Nitrate is regulated because high concentration may produce infant methylmegalopenia, which is the blue baby disease. Okay? So this is equivalent to the blue baby disease. Okay? Well, the baby will have a blue color in their skin which means that they are not getting enough oxygen because this nitrate is starting to be toxic to babies. So they have to regulate nitrate in surface water. Sulfur also can occur as sulfates, CaSO4, Na2SO4, and MgSO4, and reduce sulfide, H2S and HS-. Of course, sulfide can be found in water where there is a significant organic decomposition that result in anoxic conditions. We'll be talking about oxic condition once we come to wastewater treatment. Groundwater low in dissolved oxygen can contain reduced sulfur that impart objectionable odors. And also sulfates are also corrosive in concrete structures and pipes. You can see most of the pipes underground. If the water has sulfate, you can see that all these pipes will be corrosive. In this table, we have all of them. You could see the major calcium, magnesium, chloride, fluoride, iron, and manganese, nitrate, sulfur. You could just look at this table and see what is the source of calcium, magnesium, surface water, and groundwater, and what is the above 60 milligram per liter can be considered nuisance as hardness. And you can see it from constituent to another constituent, the source, the concentrations, and the significance at the end. Now, I'll give you a case study that it was found in Bangladesh, but this is a very problem to groundwater. Arsenic crisis, the global arsenic crisis. Naturally occurring arsenic is being all over some water supplies throughout the world. Unfortunately, when humans are exposed over a long period, look at this, when humans are exposed over a long period of time to only low concentration of arsenic from consuming it from water that has arsenic, several forms of cancer can develop. You have to be careful. Arsenic in water means cancer can develop. Of course, the WHO has accordingly set the drinking water guidelines of arsenic to 10 part per billion. This is the max. You cannot go beyond 10 part per billion. These are the guidelines by the WHO. The magnitude of the problem is most serious in Bangladesh and the West Bengal, India. In 1970-1980, 4 million hand pumps wells were installed in Bangladesh and India to provide people there with a pathogenic-free drinking water supply. So it's a hand pump well to provide water that has no pathogenic-free drinking water supply. The only problem that arsenic start to begin to appear in their water in 1980s. Shortly after the well installation programs, they put these wells, these pumps, to pump water from the groundwater for people to drink good water without microbial effect. But then they start seeing that there is some arsenic in the water. By the early 1990s, it was determined that the arsenic poisoning was originating from these wells. Today, every day in Bangladesh, up to 57 million people are exposed to arsenic concentration greater than 10 milligram per liter. Do you remember the guidelines of WHO? Not more than 10 part billions. Now they are getting 10 milligram per liter. That's huge. That's huge. In the West Bengal, India, an estimated 6 million people are exposed to arsenic concentration. Look at this, 50 to 3,200 milligram per liter. So people are dying of cancer because of arsenic in West Bengal and in Bangladesh. Of course, the magnitude of the problem shows why some have called this the greatest mass poisoning of humans that have ever occurred. There is some good treatment options now. So, the most commonly used arsenic removal system in developed and developing world are based on coagulation, separation, and adsorption processes. You coagulate these arsenic molecules in water and make them precipitate, and adsorption processes. Of course, there is membrane filtration, such as reverse osmosis. Nanofiltration is also used to remove arsenic from water. However, it is not practical because of the high cost of the RO and the nanofiltration. Let's look at this pump. This is the wellhead arsenic removal unit that they put. This is the pump. Okay, and they are pumping the water. And this groundwater has arsenic contaminated groundwater. And this is the groundwater levels. And now they put the system, okay, into every well, okay. This unit is packed with granule activated ammonia to absorb all the organics, to absorb all the arsenic from the groundwater. So you have granule activated ammonia. This removes the arsenic from the water, absorb it. And this unit can be taken. You could take this once all the units inside has been full capacity. You could take the granule ammonia, and then we could do regeneration with caustic soda about every 4 months, and you put it back for new adsorption. Because these sites, this granule activated ammonia will, let's see, you have open sites inside, it will absorb the arsenic outside and inside. Once all these sites are full, that's it. You need to take it out, regenerate, and put it back into this box unit. And of course, once we regenerate and take these arsenic particles out, or we call it arsenic-laden sludge, we lined it with bricks because we don't want this to leach back to the groundwater. Major organic constituents. Of course, organic constituents can find in water that can be either naturally occurring or associated with human activities. The major one is natural organic matter in water. This is a result of complexation of soluble organic material derived from biochemical degradation of vegetation in the surrounding environment. NOM is measured at the total organic carbon. This is famous, TOC, total organic carbon. Typical TOC values that can range from 0.1 to 2 milligram per liter in groundwater, and 1 to 20 milligram per liter in surface water, and 0.5 to 5 in seawater. NOM has a very bad effect in water treatment. If there is natural organic matter, oh, look at the effect. Of course, it will affect disinfection. It will affect disinfection. Because NOM will react with and consumes disinfectant. Our main purpose for disinfectant, that all these disinfectants will be used to kill bacteria, to kill microorganisms, to kill viruses. Okay? But the problem is that this NOM will react and consumes disinfectants. We meant this to kill bacteria and microorganisms, but NOM will take it, and that's not good. Which increase the required dosage to achieve effective disinfection, which means we have to add more. For example, we should have more chlorine. That's not good. Also, NOM will affect coagulation. NOM reacts and consumes coagulants too. Not only disinfectants, also coagulants too, which increase the required dose to achieve effective turbidity removal. Also affect adsorption. The problem with this NOM, it will absorb the activated carbon. We meant this to absorb organic matter, to absorb arsenic. But NOM will absorb the activated carbon. That's not good, which deplete the absorption capacity of the carbon. Also, NOM effect on the membranes. If you have like a membrane unit, NOM absorbed to the membrane. So you have a membrane, and of course there are small holes in the membrane to allow the water with turbidity, the water with high organic matter to pass through, and these organics are clogged on these openings. The problem is that this NOM will absorb to the membrane, clogging membrane pores and fouling surfaces. This will make what? Decline in water pass through the membrane, so everything will stop. Nothing will go past by the membrane. Because of what? Because of NOM affecting the membranes. Also, distribution system, the pipelines under the ground, NOM may lead to corrosion, slime growth in distribution systems, especially when oxidants are used during treatment. NOM is bad. We need to take care of it because it has the following effect on treatment processes. Microbial constituents in potable water, the water must be free of pathogenic microorganisms. Let's look at one of the problems. WHO reports that diarrhea contributes to 4.7% of global burden of disease in 2011. 4.7%. It's higher than any other diseases. Of that 4.7%, approximately 88% was caused by unsafe water, sanitation, and hygiene. 88% from water. Let's look at what is the meaning of pathogens. There is many classes of microorganisms, among them viruses, bacteria, protozoa, and helminths. Let's look at the small size of these pathogens that can prevent their removal via conventional gravity sedimentation. Because of their small size and because of the density of this small size pathogens, they can settle. Because remember, the density of the water is almost 1, and you need something higher than 1 for it to settle. If it's less than 1, it will be still suspended. And these pathogens are very small. So gravity sedimentation cannot remove pathogens. And of course, there is some indicator organisms such as chloroforms, and this have been identified as a very good indicator to monitor microbial water quality. Of course, there is thousands of microorganisms. There is hundreds of viruses, protozoa, and helminths. Are we going to measure each one of them? No. We will use this chloroform to indicate what is the value of the microbial water quality in water. At present, EPA requires water utilities to monitor their water distribution system monthly for total chloroform. Okay? The total chloroform rule maximum contaminant level is based on frequency of detection. How many times? No more than, look at the regulation. No more than 5% for system collecting at least 40 samples per month, or combination of positive E. coli sample or fecal chloroform with a positive total chloroform sample. This is the regulation by the EPA. This table shows representative pathogenic organisms in raw water samples. Like, let's say the pathogens, Vibrio cholera. The shape is worm-like. The size 0.5 to 1 to 2 micrometer. Very small. You can't even see it. This type of pathogens is bacteria type. What is the health effect of this pathogen? Of course, classic cholera, which is an explosive diarrhea, vomiting without fever, followed by dehydration, abnormally low blood pressure and temperature, muscle cramps, shock, coma, followed by death. Normal habitat, it could be found in human stomach and intestines. The next pathogens is Salmonella. Shape, rod shape. This is a worm-like. A worm-like. This is a rod shape. Rod shape. It's like a rod. Size 0.6 micrometer. This type, Salmonella, is a bacteria type. Okay? Like Salmonella typhi species cause enteric fever, headaches, malaise, and abdominal pain. The normal habitat is in intestines of warm-blooded animals. Shigella density. Shape is round. Size is 0.4 micrometer. Type bacteria, still. Bacillary dysentery, abdominal pain, cramps, diarrhea, fever, vomiting and blood, and mucus in stools. this normal habitat is human stomach and intestines. See, they know exactly from where each one of them are coming. E. coli, its rod, size is 0.3 to 0.5 by 1 to 2 micrometer. Type bacteria. Of course, E. coli is diarrhea. Normal habitat is intestines of warm-blooded animals. The next one is bolivirus type 1, 2, 3, round, size 28 to 30 nanometer. Look at this size, nanometer, very small. This type, virus, fever, severe headaches, stiff neck, back, deep muscle pain, and skin sensitivity. Of course, normal habitat is human intestinal tract. We'll keep going. Human adenovirus type 2. The shape is 12 vertices, size 70 to 90 micrometer. It's a virus. Human adenovirus, severe infection in lungs, eyes, urinary tract, genitals. Some strains affect intestines. Of course, this is human. Rotavirus A, round and size 80 nanometers, is virus, severe diarrhea and dehydration. Humans. Cryptosporidium baravium, type 1 oocyst, shapes is ellipsoidal, size 3 to 5 micrometers. And of course, shape is, there is another type of this is sporozoites and merozoites. Shape is worm-like, size from 10 to 1.5 micrometer. This is protozoa. Severe diarrhea, abdominal pain, nausea or vomiting, and fever. Of course, humans. Gardia lambalia, single cell shape, is flagellate protozoa with the flagellates, with a tail, size 9 to 15 micrometer long, 5 to 15 micrometer wide, and 2 to 4 micrometer thick. Protozoa. Sudden diarrhea, surprised, abdominal cramps, bloating, cramps, and weight loss. Humans again. The last one is these eggs that comes as a worm-like organism, helminths. Of course, this will cause squamous cells carcinoma of the bladder. Of course, it will have a urinary tract infection, urethral and uretary structures with subsequent hydrocephalus and renal failure. Very bad. This can be found in blood vessels of the human bladder and in mammals. There's a big list, and the book describes few of them. And of course, there is like a year of studying for these types, and how could you analyze each one of them, and what are the effect on human health, and where did they come from. But we took these two slides, the previous two slides, to show some of these bacteria, virus, and protozoa. Now, because all of this, organic, inorganic, and microbial life in water, we need to have a standard. We call it water quality standard. Of course, the main purpose of the water quality standard is to protect public health. Of course, the Environmental Protection Agency established a primary drinking water standard by setting health-based maximum contaminant level goals, MCLGS, and of course, maximum contaminant levels, MCLs, for a large number of pollutants. So there is MCLGS, maximum contaminant level goals. That's what we're expecting to do. And MCL, the maximum contaminant levels for a large number of pollutants. Now, let's call this MCL is enforceable standard. And it's based not on health and risk assessment information, but also in the cost and the availability of the technology. The MCLGS are based solely on health and risk assessment information. This is the goals. Let's look at a standard that my file. Look at this. This is the maximum contaminant level goal. And this is the maximum contaminant level. So this is the enforceable. This is the future goals. Okay? And of course, MCLG are based on health and risk assessment, and MCL are based not only in health and risk assessment, but also in cost and availability technology, money and the technology if it's available. Let me just, I'm not going to go through all these chemicals. I'll choose, for example, lindane. It's a chemical, a synthetic organic chemical, and see the way they abbreviate synthetic organic chemical, SOC. The maximum contaminant goal is 0.0002 milligram per liter, and the MCL, maximum contaminant level, is 0.0002. Let's look at this polychlorinated biphenyl, BCBs. This is also a very important synthetic organic chemical. The goal is to make it zero, but do we have available technology? Do we have the money? This is the goal, okay? But now the maximum contaminant level is 0.0005 because, of course, not only health here, not only risk, but also technology and money availability. So we have all of this. So this is the goal. This is very difficult to reach right now, maybe in the future. Let me give you another example of volatile organic chemical. Look at the way they abbreviated VOC. I'll give you, for example, benzene. It's one chemical that might be called volatile organic chemical. Let's look at the first one. MCL, maximum contaminant level, 0.005. What was the unit? Milligram per liter. While the goal is to make it zero in water. Let's look at an inorganic, arsenic. The goal is zero, but now the MCL is 0.01 milligram per liter. We will try to do the overview for the water treatment process and then stop for the next video. This table 8.9 gives you the processes that might be used to treat water. The first constituents of treatment options. Treatment, the constituent that we want to treat is turbidity and particles in water. How could we remove this? We need coagulation, flocculation. We'll be talking about these processes in the next video. And also sedimentation process are good to treat turbidity and particles together. Granule filtration is also another unit process that use to treat turbidity and particles. How about major dissolved inorganics? Very tough to remove using coagulation, flocculation, sedimentation, and granule filtration. Now, for this major dissolved inorganic, we need softening, aeration, and membrane. The minor dissolved inorganics, membrane. Pathogens, sedimentation, of course, filtration, disinfection to kill them. Major dissolved organic, membranes, and adsorption. We'll be doing this in the next slide.